And this is my video number 17. Video number 17, the stability of the linear system. Stability of linear system. Okay, we consider the system. We are still in the non-autonomous, which is the function depend on t. So we consider the system x dot is equal to a t x. That is system. Yeah, where xt is a unknown vector x, which is a function of t, which is, you can consider this as a x1 of t and so on, xn of t as unknown function. And the matrix at with the element a ij of t, this is continuous for t not t goes to infinity. Okay, and let's call this, let's give a name to this equation. For this particular video, I call this equation number 1. Okay, we recall the equation, the solution of system 1, and the solution of 1 satisfying x t naught is equal to x naught is then defined for t greater than t naught and is given by x t naught x naught as a phi t x naught, where phi t is a fundamental matrix. Fundamental matrix satisfying phi t naught equal to I. Okay, now I define the norm as I promised before, that we're going to define what we mean by a norm of a matrix. We are given the n by n matrix A with components or element aij, where this is of size n by n. Then the norm defined as the norm of A, you define as we sum all those elements of A with modulus for each I and j. Okay, so this is the definition for norm of the matrix A. A is a real valued non-negative function defined on the set of n by n matrices. Norm of A, this norm of A is a real valued non-negative function defined on the set of n by n matrices, and if AT is continuous, then the norm of AT is also continuous. And in addition to that, the norm satisfying summation of matrix AB norm, this is less than norm of A plus norm of B. And for multiplication of matrix AB less than norm of A times norm of B. And number 2, for any scalar C A, this is equal to C norm of A for any C scalar. And 3, we have AX, this is less than AX for any vector X, for any vector X. So in general, the notation of stability of a solution and boundedness of a solution are independent. So the stability of the solution, boundedness of the solution are independent. The stability of a solution and the boundedness of the solution are independent. What does it mean? So in general it is like this. For the special case it's different things. Now in general we have the stability of the solutions and boundedness, which means if the solution is stable, it doesn't mean the solution is bounded, and vice versa. If the solution is bounded, doesn't mean the solution is stable. But of course, if you have the result for the case of linear system, for the case of linear system is different story. For the case of linear system, I give you the example for this first. If you have let's say the solution x t plus x naught, this is the solution of x dot equal to 1. So in this case, this is of course definitely this is a stable solution, but as t goes to infinity, so you can see this x also goes to infinity, so it's unbounded. So we can see from here, for this particular case, it satisfies this thing. Yeah, the solution is stable, but it's not bounded. But for the case of linear system, yeah, we have a theorem for that. For the case of linear system, so all solution of one, yeah, all solution of one are stable if and only if they are bounded. They are bounded. There is a proof in your notes. I'm not going to prove all, yeah, all the theorem, but in this case, I think I can prove this one. Okay, so to prove this theorem, let's say the solution is bounded. So it means that we prove from right to left, this direction. So we assume the solution is bounded. Yeah. Assume first the solution is bounded. Yeah. Solution of one, of course, are bounded. So what does bounded means? Bounded means there exists. So which means there exists a positive number m, say, such that the norm of phi t, this is less than m, where phi t is a fundamental matrix. Yeah, this phi t is fundamental matrix, satisfying that the definition I given earlier, that phi t not equal to the identity. Okay, then what we need to show is that we need to show the solution is stable. Yeah, the solution is stable means that if you take the norm of x minus x naught for any x naught and x1, we must show that those norm must less than epsilon. Refer to the definition given in the previous video. Now, given any epsilon, yeah, given any epsilon positive, then we may choose the difference of x naught minus x1 less than epsilon over m. So why do we choose this? It depends on our next line, which implies that we have the difference between x or the norm of t naught and x naught, and x t naught and x1. And we know that because x is satisfying phi x, so we have this one, this is equal to phi t x, we have x naught minus x1, so x naught minus x1. Alright, so this is less than phi t x naught minus x1. We know that this one is phi is less than epsilon from our assumption. Alright, and then we choose x minus x naught so that we have that norm less than epsilon. So that's the purpose. So that's why here in this case we choose x1 minus x naught minus x1 less than epsilon over m, so that we have this, we have less than m x naught minus x1, like say absolutely less than m. Then we may choose x naught as that, so therefore we have m epsilon over m, that give you epsilon. So this shows that when the norm of that less than epsilon, so the solution is stable. Yeah, so therefore the solution are stable. So we have proved this theorem from right to left. Means that given the solution is stable, or if you can show the solution, if you can show the solution is bounded, then we can conclude that the solution is stable. Now, to show the solution is stable, and then with the stability of the solution, you can conclude that the solution is also bounded. You have to begin with the that less than epsilon, okay, and then we show that M is the solution is bounded. Now, for that direction, which means stable, solution is stable, then bounded. So we suppose that all solutions are stable. All solutions are stable. Solution to system 1. Then the solution x t naught, where x naught is 0, this is 0, is stable. Okay, so we consider that case. Therefore, given any epsilon, given any epsilon positive, we can find delta such that the norm of x1 is less than delta. Why x1 here? Because we have x0, we have x0 minus x1. So we take this is less than delta, but this one is 0, so that's why we have x1. So that less than delta. So we have x1 less than delta, which implies that we have our x t naught x naught is 0, so we have 0 minus x t naught x1, that gives us phi t x1, okay, and this is less than epsilon. Why less than epsilon? Because our solution is stable. So now we need to show that our solution is bounded, which means the norm of phi less than some positive numbers. Okay, so you may consider because x is the vectors, so we may consider the rows of I, of certain rows we have a values, but others are 0. So those, let's consider those value is delta over 2. That's our choice. So if we choose now x1 to be delta over 2, the element of vector x, one of them is delta over 2, the rest is 0. Then we have phi t x1, this is less than phi t x1, so this is since we take x1 is delta 2, so we have phi t delta over 2, and this is less than epsilon, because from there. This is less than epsilon, so we have that less than epsilon. Okay, so therefore you can write phi t. So therefore we can have phi t. This is less than 2 epsilon over delta. Okay, then this gives you a number. So let's call this number is k. Alright, so therefore we have x t naught x naught, then the solution which is the general form. We have phi t, the fundamental matrix, x naught. Alright, this is less than phi t x naught. Alright, and phi t we should have less than k, so this is less than k x naught. And so which means the solution is bounded. Hence all solutions are bounded. And we note that the characteristic polynomial of a constant matrix is stable if all negative if all roots have a negative real part. This we have done in the when we consider the autonomous system. Yeah, we recall that the characteristic polynomial, which is the determinant of a minus lambda I of a matrix A is said to be stable if all its roots have negative real parts. All its roots have negative real parts. Okay, so we have a theorem. I don't want to prove the theorem. It's not difficult. You can follow the solution, the proof from the note. I just give you the theorem. Okay, the theorem. So that if the characteristic polynomial of A is stable, if the characteristic polynomial of A is stable, then every solution of x dot equal to ax is asymptotically stable. Okay, so I'm not going to prove this. Now, in order to prove, if you want to study the proof of this, remember that the asymptotically stable means if we take the for the solution of order t, if we take t goes to infinity, then the solution should goes to the critical points. So that's the asymptotically stable. And also you have the definition of the difference between x naught and x1 is less than epsilon for any big T. Yeah. Okay, and I have another theorem that again, I don't want to prove. Okay, I give you another theorem before I give you the example. We have a theorem. If multiple root of the characteristic polynomial of A have negative real parts and the root of multiplicity 1 have none positive real part, then all solutions are bounded and stable. Yeah. If the multiple roots of the characteristic polynomial of A, of the characteristic polynomial of A have negative real parts, and the roots of multiplicity 1 and the root of multiplicity 1 have non-positive real parts. 1 have non-positive real part, then all solution of x dot equal to ax are bounded and hence stable. Okay, so we have a couple of results for the stability of the linear system. Yeah, the quite important one, which is if the solution is stable, then bounded, and if bounded, then stable. And also on the characteristic polynomial, yeah, A stable, then the solution is asymptotically stable. Those are pretty important when we deal with when we want to solve the problem. Okay, so I think for this video I stop here. Right, continue to the next video. Thank you.